Welcome to the video tutorial on interrupted time series. This is the second part of a three-part series that illustrates how to evaluate routine data using interrupted time series. In the first part of this video tutorial, we review the interrupted time series analysis, or ITS for short, steps needed when using this method, and prepare the routine data set for analysis. In this second part, we will focus on single group interrupted time series, and part 3 will be on multiple group interrupted time series. In the single group interrupted time series, we only have one group or cohort that experienced the event or program or policy. And for both types of interrupted time series, we would need to have two segments. We'll need to have observations before the intervention and observations after the intervention. And if you remember in the previous video, we said we'll need to have a minimum of 8 time points or observations before and 8 times points after. And so you'll need a minimum of 16 time points in order to run an interrupted time series analysis. So as we mentioned previously as well, ITS uses a regression-based technique for the analysis. And the regression model for our single group ITS is what we see on the screen now. In our equation, Y is an aggregated outcome measured at point T. T is the time since the start of the study. X is a dummy variable indicating whether we had the program or policy when we didn't have it. So our pre or post-intervention periods, where our pre-intervention periods are when we don't have the program or policy, is indicated by 0, and our post-intervention, which is when the policy or intervention is being implemented, is 1. Our XT is an interaction term of our dummy variable for our pre and post period, and also RT. And it basically tells us the time after the intervention. And epsilon is our error term. So you also notice in the equation we have coefficients, and in our equation those are in black. B naught is the intercept or starting or existing level of the outcome at the beginning of the series. Beta 1 is the slope or trend prior to the intervention. Beta 2 is a change in the level of the outcome that occurs in the period immediately following the introduction of the intervention. It's also the immediate effect of the intervention, and it provides information on the level change after the intervention. Beta 3 is a change in trend in the post-intervention period. It's basically a difference in the pre and post-intervention slopes. And significant values in beta 2 indicates that the immediate treatment effect, and beta 3, significant values in beta 3 indicates the treatment effect over time. And so this is a visual representation of what we would produce as a result of getting the different coefficients in our regression. So if you see our beta naught, which is our existing level, is our intercept. The slope of the pre-period is our existing trend. The change in level is our beta 2. So this is what we see immediately after the policy change or intervention. And the slope of our post-intervention is our beta 3, which is our trend change. In order to complete the interrupted time series, we'll need to generate some variables in order to fit the model. And these are the variables that we talked about in our regression model. So our T, which we call time, X, a program or interventional policy, and XT is a time after the intervention. And so this slide presents a sample data set after these variables have been generated. In the first 2 columns, we have the year and the constituents and our rate variables. The rates are observations or data collected to determine the effect of the policy or program or intervention. Our T, which is our third column, tells us the time or number of data points. Our X indicates the pre-period and post-period, or whether we have an intervention or whether we don't have an intervention. So our 0 indicates pre-periods and 1s indicate post-periods. And our XT is the time after our intervention. So all pre-intervention dates will have a value of 0, and we start counting the number of observations after the intervention. And so in this, we know 2009 is when the intervention or policy change happened in this sample. As a reminder, we are going to go through the steps of the interrupted time series using a fictional example. Our data comes from Exile, a fictional country. In November 2017, Exile introduced a policy that eliminated fees at health facilities associated with maternity care services, with the aim of increasing the utilization of health services and ultimately improving maternal health outcomes. The policy was piloted in 2 constituencies, Gold Coast 9 and Gold Coast 15, and we received our health facility data on the number of women who attended their 4th ANC visit from 2017 to August 2020 specifically. So in part 1 of this ITS video, we prepared our data set by aggregating our data to the constituency level, formatting our counts to rates, reshaping our data from wide to long, and finally formatting our dates to be recognized by data. And so as of now, we have 6 variables and 132 observations in our data set. Our variables include ID, which is the unique identifier for each constituency, a region variable that tells us the region the constituency is in, our constituency variable that tells us the different constituencies in our data set, the number of health facilities in each constituency, and our date variable and the outcome variable, which is the consistency rate of 4th ANC visits. So this is a visual of our sample data set and a list of variables just as we had described in the previous slide. We want to answer the research question, specifically the first one. What was the impact of the policy on the utilization of ANC, specifically 4th ANC visits of pregnant women in Gold Coast number 9? As we mentioned in the previous slide, our policy was implemented in November 2017. So our time points will be pre-November 2017 and post-November 2017. So before moving on, I also want to point out that the outcome variable in this case is the 4th ANC visits, so constituency rates of 4th ANC visits in Gold Coast number 9. As a reminder, there's several steps that are needed to use interrupted time series, and we first need to determine the time period. So we know that our policy was implemented in November 2017, and we'll talk about the other time periods in the next couple of slides as well. So keeping in mind that our policy was implemented in November 2017. From our research question, we know what our analytic sample is. And since we only have 1 cohort, we don't have to worry about the control and all of that for now. Our outcome of interest is the utilization of ANC, as we mentioned previously, specifically the constituency rate of 4th ANC visits. After, we'd want to visually inspect the data. And during this inspection, we want to look for well points, linear trends, and any other data quality issues. Next, we want to perform a preliminary analysis and also check for autocorrelation and address it if present. Then we'll run our final model, plot our results, and predict the relative and absolute effects of our intervention. Going on to the first step, which is determining time periods. So in doing so, we'll need to identify the pre and post period, time since the study started, and then also the time after the policy began. And so our regression equation is going to be useful in doing this. So we know that our Y is our outcome, which is the constituency rate of 4th ANC visits. And we need the Y because the rates of our observation data that was collected, and it's going to help us determine the effect of the policy. Our T tells us the time or number of data points since the start of the study. So in our example, each month is an observation. And so we want to count the number of months starting from January 2017. X is our dummy variable indicating our pre and post policy. So in our pre-period, we didn't have a policy in place. So we're going to indicate it as 0 or assign it a value of 0. And in our post periods, when we did have the policy in place, we're going to assign it a value of 1. Our xt, the interaction term between time and our dummy variable, tells us the time after the policy started. And so all the pre-intervention or pre-policy periods will have a value of 0 and will count the number of observations after the policy's introduction. So after the policy's introduction from November 2017. As we said previously, we want to include our time period and post-time variables in our data set. So our T is our time, our X is our period, and XT is a post-time variable. In Stata, we have our M date, which tells us the year. We can include and declare this in our data sets, which is the next step we would have to do. But to use this end date variable, we would have to identify the month in the Stata internal format. And as you may recall in the previous video, we converted our dates from the Stata internal format to the human readable format. So if you want to use the end date variable, you'll need to know the Stata internal formats for each time period in order to use it and to run your interrupted time series. Alternatively, you could use the time variable that we will create, and it will count the number of observations. So each month will count as an observation. And so we'll sort our data and then generate the time variable. We'll also create the dummy variable that indicates a pre and post policy period and call it period, as we mentioned previously. And then we'll have a variable representing the time after the policy and call it post time, as we mentioned previously. And on the right is a visualization of what we would want the new variables we're going to create to look like. So we successfully created our time period and post-time variables using the command on this slide. For the time variable, we sorted our data before creating the variable that counted the number of observations for each constituency. For the period variable, we assigned pre-periods a value of 0 and post-periods a value of 1. And lastly, for our post-time variable, we counted the number of observations after the policy introduction. We considered the month the policy was introduced as month 0 and then assigned pre-periods values of 1. And so going forward, we're going to use the time variable that we've created. But note, you can also use the end date variable because it provides the exact same information, but it's just presented in another way. This is what our data looks like, and I'm only listing the observations for one of the constituencies in the data set, specifically Gold Coast 9. So in our data set, we added 3 variables from what we started with. So we now have 9 variables. And I want us to remember that November 2017 is the 11th observation or data point in the time variable. And so this is important going forward. So before we can start our analysis, we must first declare the data set to be a time series data set using the tset command. And if the data set does not contain multiple panels, then we'll have to use the tset time variable. So if you look at the tabulation on the right, Gold Coast number 9 is the only constituency listed. And so assuming this was the case, we would only have one panel variable. And so we would use the tset time var. But our data set contains multiple panels because it has 3 different constituencies. And so we'll have to declare the panel variable, which is our consistency variable. So in the tabulation on the right, we notice we have Gold Coast number 9, North Troy listed. So 3 different ones, 3 different constituencies. So we have to declare our panel variable when we declare the data. So we'll use a tset panel var time var command. And if we don't do this, data will tell us that there are multiple time entries and the command will not work. With our panel variable, which we know we have, because we have multiple constituencies, this was the output we produced. And so as we know, we said we could use either end date or time. And so we are choosing time, but just keep in mind that if you do decide to use end date, you would have to know the Stata internal form of the monthly dates and use that in the subsequent commands for the ITS analysis. So going forward, we are using tset constituency time to declare our data. Next, we want to conduct a visual inspection. This step can be done before declaring the data sets as time series as well. And you can use two-way graphs to do this, either the connected line plot or the line plot, and the choice is entirely yours. For both, you'll need to know your dependent variable, your independent variable, the year the policy or interruption occurred. So in our case, our independent variable is time. Our dependent variable is our constituency rate of fourth ANC visits. And our policy occurred in November 2017, which is the 11th time point in the time variable. So we went ahead and used the connected line dots, indicating our outcome and time variable, as well as the constituency of interest because we have multiple constituencies in our data set. We asked data to draw a red dashed line at November 2017, which is our time 11, so we know when the policy occurred. We labeled our x-axis, y-axis, gave the graph a title, and the graph we see is what was produced. So inspecting it briefly, we can see that there's a linear trend before the intervention started and an increase after. There doesn't seem to be any missing data. Something must have happened between August to October 2018. And we'll need to take, and in order to re-understand this, we'll need to take a step back to review our records to see what was happening in Excel during that time period. And also in January 2019, there's something that happened that caused the rates of visits to increase. To analyze our interrupted time series, we'll be using the ITSA command developed by Ariel Linden in 2015. It can be used for single and multiple group into ITS. It's used to control for autocorrelated disturbances and estimate the treatment effects over multiple periods. To use the command, you'll need to identify the following. You'll need to know your outcome variable and independent variables if there are any. And your outcome variable must be ordered as a time series. The command allows you to weight the data, but will not be doing this. The treatment period, TR period, specifies a time period when the intervention begins. The values entered must be from the time variable that we used when we declared our data set. Single tells the data that we're running a single group analysis, and when you omit the word single, it runs it as a multiple group analysis. Treat ID specifies the identifier of the single treated cohort within the data set, especially if you have multiple panels. The value entered must be the same, or it must be from the panel variable used when the data set was declared. Our lag number is the maximum number of lags to be considered in the autocorrelation structure, and the default for ITSA is 0. Including figure tells data that we want to produce a line plot of predicted dependent variable combined with a scatter plot. And so we'll produce a graph similar to what we had seen previously when we talked about the regression equation for interrupted time series. A few slides back, we also mentioned that we created the time period and post-time variables. So ITSA automatically generates these commands as part of the output. So you would need just a time variable. You wouldn't necessarily need to create the period and post-time variable. And so the replace component of a command replaces these variables if they've been created previously. So if you run the ITSA command previously. And so if you want more information on the ITSA command, you would search help ITSA inst data. Just as a reminder, this is a regression for a single group ITS and the graph that we would want to produce once we run it. For our preliminary analysis, we run our ITSA command assuming no autocorrelation, where our lag is 0. We specified our outcome variable constituency rate of fourth ANC visit. We included single because we're running a single interrupted time series analysis. We indicated the unique identifier for Gold Coast, which is the number 20, and the policy was implemented in November 2017, and this is the 11th time point in the time variable. As I said previously, we're assuming no autocorrelation, and we specified figure because we want data to produce a graph as part of our output. So once we run our ITSA command, we produce the following output, which we also present as a table because it's a little bit clearer. So our intercept, which is underscore cons, which is the last row, gives us our beta naught, which is the level at the start of the study in January 2017. On the first row, we have underscore t, which is our beta 1, and it's the existing slope or trend during the pre-policy period. On the second row, we have underscore t11, and that is our beta 2, which is the level change immediately after the policy. And then on the third row, we have our beta 3 underscore x underscore t underscore 11, which is our slope change after the policies. This is the slope during the post-policy period. And so from what we can tell, all our p-values are less than 0.05, and they are significant because of this. Our findings suggest that the starting constituency rate for fourth ANC visits per month was estimated at 0.133%, and the constituency rate increased significantly every month prior to our policy, which was implemented in November 2017, by 0.0033%. After the policy, there appeared to be an increase in the constituency rate of fourth ANC visits per month of about 0.311%, and an increase in the trend of the consistency rate of ANC visits by about 0.011% per month. And this increase in the trend in the post period is relative to that in the pre-policy period. And so on the next slide, we're going to see the graphical representation that we got by adding the figure to our command. Just to go over, our beta naught is our intercept and it's our existing level. The slope during our pre-policy period is our existing trend, which is what we got at beta 1. Our level change is the immediate change when the policy was implemented, and our slope during the post-policy period is our trend change of beta 3. So as part of our analysis, we want to assess for autocorrelation. And to understand why we're assessing for autocorrelation, we need to understand what it is. So it is a degree of similarity between a given time series and a lagged version of itself over successive time intervals. It occurs in time series studies when the errors associated with a given period carry over into future time periods. And so overestimating 1 year is most likely going to lead to an overestimation in the following year and vice versa, where underestimation in 1 year will lead to an underestimation in the following year. So we'll need to assess for autocorrelation, and it will also give us more accurate estimates of our standard errors and confidence interval. And there are multiple ways to assess for autocorrelation, and all of these ways are post-estimation commands, so we run them after our ITSA. We'll focus on the first in the list, so the Huizinga test for autocorrelation, the AC test. And so you can specify the variable name after AC test, but we want to assess it off the previous regression, so we're not including this. And we'll specify the number of lags we want Stata to give us. If we specify 12, it will show us the output for 12 lags and so on and so forth. And so for visual assessments, you can run either the correllogram, the autocorrelation plots, or the partial autocorrelation plots. So the correllogram gives you both the autocorrelation plots as well as the partial autocorrelation plots. But if you want to see the ACF or the partial ACFs on their own, there are commands to do that as well. And for this analysis, we're focusing mainly on the Huizinga test for autocorrelation. We run our test, and this was our output. So in our Stata command, we asked for 10 lags. To interpret the test and determine where a lag is present, you want to focus on the level of significance on the right side of the output. And for each lag, autocorrelation is present when the p-value is less than 0.05. So if you look at our first lag, our p-value is 0.001, and this is less than 0.05, so we know it's significant. Our second lag, our p-value is 0.331, and this is less than 0.05, so we know it is significant. And our third lag, the p-value is 0.0363, and it's less than 0.05, so we know it's significant. And from lag 4 and any higher lag orders, the p-values are greater than 0.05, so we know it's not significant. Thus, when we run our final model, we will specify the maximum lag as 3. So in the final model, the only thing we changed in our command was the number of lags to account for autocorrelation. So this is our output and a tabulation of the content of the output. Our coefficients remain the same after accounting for autocorrelation, but you'll notice that our p-values and 95% confidence intervals changed slightly because we did account for autocorrelation. And so now we have a more accurate estimate of these. And after accounting for autocorrelation, our coefficients still remain significant. And so our interpretation is pretty much the same. And so the starting constituency rate of fourth ANC visits per month was estimated at 0.133%. And the constituency rate increased significantly every month prior to November 2017 by 0.0033%. And after the policy, there appeared to be a significant increase in the constituency rate of fourth ANC visit per month by 0.311% and an increase in the trend of fourth ANC visits of about 0.011% per month. And this increase in the trend during the post period is relative to the pre-policy period. And this is a graphical representation of our analysis. And again, from our preliminary findings, we know that this is our intercept, which is our existing level before the start of the study. Our pre-period slope is our existing trend. This is our level after the intervention and is the immediate change after the intervention was implemented. And our post-trend slope is at the trend after the policy was implemented. And so from this, we can say that as a result of the policy change, there was a sustained increase in the constituency rates of fourth ANC visits by about 0.3% and an increase in the trend by about 0.01% per month. So in addition to determining this impact, is it possible to conduct further analysis to calculate the impact at specific time periods? We're interested in calculating the impact of the policy a year after. And in doing so, we want to calculate the absolute change and relative change. And to calculate these two changes, we'll need to know the fitted and counterfactual values. Our counterfactual is basically what happened to the outcome or to the constituency rate in the absence of the policy. So if we didn't have this policy, what would our rates be? And our fitted value measures what happens when we have the policy. And when you find the difference between the fitted and the counterfactual at the specified time period, it will give you the absolute change. And when you take the absolute change and divide it by the counterfactual, that will give you the relative change. And we're going to go through the calculation of these fitted and the counterfactual in the next slides. In predicting our counterfactual and our fitted value a year after the policy, our regression equation is going to be helpful, and we're going to focus on any time-related variable just to start with, specifically our t and the time variable and our post variable, our t and the t and the xt. So we know that we want to predict a year after the policy. Our policy, we want to first calculate the time since the policy started. Our policy was implemented in month 11. So we know it's been going on from the first month all the way through month 11. And we want to know the impact 12 months after the equivalent of a year. So 11 plus 12 gives us 23. And the t and the xt is the time since the policy starts. And so we know our policy, we're going to everything pre-policy is technically 0. So we'll start counting after the policy has implemented. And so 12 months later, we're basically looking at time point 12 in the xt variable. So to predict the counterfactual, we're assuming that the policy wasn't in place. So we don't have this policy. So our x is equals to 0, our t is equal to 23, our t and the xt is equal to 12. And so taking the regression equation and putting in the necessary numbers that we have for x and t, and then the t and xt, we reduced our equation to beta naught, which is our existing level, and adding the existing trend and multiplying the existing trend by 23. And that will give us a counterfactual at 1 year. And so when we run it in Stata, Our absolute change is 0.0020894. So for our fitted value, it's what happens when the policy is in place. So our x is equal to 1. Our t is the same as what we use for the counterfactual, 23, and the t in the xt is equal to 12. And so putting all these in the regression equation gives us the final, we simplify it to our beta naught, which is existing level, plus our existing trend, or beta 1, multiplied that by 23, plus our level change, which is our beta 2, plus our trend change, which is our beta 3, multiplied by 12. And when we put this in stata, our output was 0.0065666. And so once we plug in all the numbers, we find out that our absolute change is 0.00448 and our relative change is 2.14. And if you want to think about it as a percentage, you multiply these numbers by 100. And so we can say that in the first year after the policy, the constituency rate of fourth ANC visits was 0.44%, more than would have been expected if the policy was not implemented. And this represents a 214 percentage point increase. To summarize, in our single group ITS, there's only one cohort, and this cohort experienced the event, interruption, intervention, or policy. The it's a command that we've talked about can be used for single and multiple group comparisons. It controls for autocorrelated disturbances and estimates the treatment effects over multiple periods. And it can also produce a graph for you as part of the output. We can use the Combi-Huizinga test for autocorrelation to determine the maximum number of flags to include in the analysis. And we do this to get a more accurate estimate of our standard errors and confidence intervals. In addition, to determine our impact, we can also predict our absolute and relative change. And so this is the end of part 2 of the video tutorial on interrupted time series. We have several resources, and this is a list of what we have on the Data for Information website, our background information sheet on interrupted time series, the presentation used today, as well as the stata do file and sample data set for parts 2 and 3 of the ITS video tutorial. In the next part, we will review multiple group interrupted time series.